Great. Okay, well, welcome to the last day of the conference. We're really glad that all of you came. It's been fantastic to have all of you in the same room from a wide variety of fields to talk about black holes. And I'm going to shift our focus a little bit to isolated black holes. We spent 3 jam-packed days talking about binaries. It's time to move on. But trust me, we won't move on very far. Okay, so isolated black holes in the Milky Way are relatively simple creatures, at least at first glance, right? So you're going to see how we're going to find them, obviously, from this picture right now. Don't worry, we don't find black holes this close to the Milky Way. But they're relatively simple. The basic properties for black holes, they have a mass, they have a spin. We're astrophysicists, so they have a 3D position and a 3D velocity that we care about, right? And so if we want to study and understand black holes, we have to find them. And we have now. We've found one isolated black hole. And so my talk is done. Questions? Just kidding. Now, if you want to hear more about the detection, Casey Lamb will be speaking in the next session, and she'll give you all the gory details. But I want to talk about this from the theoretical perspective. Isolated black holes aren't born isolated. We've seen this plot 100 times in the conference. The binary fraction of progenitors to black holes, O stars, is maybe 100%. I should say multiplicity fraction, because they're usually in triples, quadruples, high order multiples. So this green zone here is where we're talking about. These are the things that produce black holes. And they all are born in these high order multiples. How do they become isolated? I really like this cartoon by Chen et al. In 2024. It shows you how all of the isolated black holes are formed, at least in cartoon form. And I've just, you're not meant to read this because it's a mess. All of the wide massive binaries are in the green zone. All of the tight massive binaries are on the left in the blue zone. But all of the red boxes that I've highlighted show you where an isolated black hole became isolated and a black hole. Okay, so unfortunately, as simple as we would like isolated black holes to be, they had a complex history. And understanding that history is part of the reason we're all here. So how many isolated black holes do we expect in the Milky Way? I thought I knew the answer coming in, at least a theoretical prediction, and then I got really confused after day 1 and day 2 with all the talk of triples and, oh my goodness, how many could stay together, how many systems could stay together for longer than we anticipate. However, what's in the literature today is pretty consistent forward modeling population synthesis with everything we know about mass exchange in binaries, not triples, but evaporation, disruptions, mergers, all leads to the vast majority of black holes living in isolation. Something like 10 to the 8 solar mass black holes should be in isolation in the Milky Way, whereas those in binaries that remain in binaries after their black holes is something like 10 to the 6. Okay, so of course, when we try to figure out what that number is and where it comes from, there's a whole lot of physics there, a whole lot of astrophysics. And that's part of the uncertainty in these predictions and why it's important to test things observationally. Let's switch to the observations. What do we know about black holes observationally? Most of it is from binaries. Gravitational waves, of course, hundreds now of stellar mass black holes merging, not in our Milky Way. The electromagnetic ones are shown in purple. They're a little bit harder to see, and they too are all in binaries. They just don't have the nice fancy lines connecting them because they don't connect with other black holes, they connect with stars. So there's the nice sample that we've seen again, same plot many times throughout this conference of the binary black hole population inside the Milky Way now. And you can see it's a lovely filled diagram. We'd like to fill it more, but I have to say it's the best case I've ever seen of the tail wagging the dog. The isolated black holes are the vast majority of the population. We're trying to understand that population from this tiny little tip of things, these rare occurrences where they actually survive. As a side note, I think people have said this several times throughout the conference, but it is very hard for all of us to put together or to get a list of all the black holes that have been discovered, and we need a better black hole archive. Right around this time in exoplanets discoveries, they made the exoplanet archive, so I just thought I'd advocate for we need a black hole archive equivalent. Yeah, I see some head nods. I'm not the only one. Okay, so given that we're only probing this sort of rare population of black holes in binaries so far, except for the one, We have a lot of really basic questions. When I think about what drove me to want to help organize this conference, it was this series of questions. Really basic ones, like how many black holes are in the Milky Way? We have lots of theoretical predictions, not a whole lot of observational constraint. Which stars turn into black holes? We've heard some fantastic talks about theoretical developments trying to take a star and turn it into a compact object and figure out what it is. But I think those physics are extremely messy, as we saw. I wish Adam was still here. We can applaud how messy they are. But whether a massive star, an O star, turns into a black hole or neutron star, we know it's not easy. It's not simple, because we see neutron stars where there should have been black holes in the Milky Way. What is the black hole mass and spin distribution? Of course, this, you might think, we have actually starting to have really good measurements of this from the LIGO population, but those are not your normal black holes. And so the mass distribution and the spin distribution may be very different for all of the rest. How many black holes are in binaries, and when will they merge? Of course, that's very interesting for connecting all of our populations we can probe in the Milky Way to those we can probe in other galaxies with gravitational waves. And how many are in these binary systems, how are they formed and destroyed? That's that big messy picture we saw before. Do black holes get kicked when they have a supernova, or even more importantly, do they have a supernova? Unclear these days. And I won't talk about primordial black holes at all, but I mention it here because microlensing and gravitational lensing has a means of probing that too. Okay, so let's get back to the observations. What's the technique we're going to use? We've heard about astrometric binary wobble. We've heard about radial velocity spectroscopy. We've heard about gravitational waves. Now it's time to talk more about microlensing, although Peter gave an excellent introduction yesterday. The outline for the rest of my talk is here in non-traditional format. When we're trying to probe black holes in the Milky Way, there are a lot of ingredients. When we first started this experiment now 15 years ago, this is what we had to, none of this stuff really existed, not at least for studies of isolated black holes, so we had to build a lot of it up. So I'm going to take you through this process a little. You had a nice introduction from Peter yesterday on microlensing, but I just wanted to show you a little bit more in depth on what it takes to find an isolated black hole with gravitational lensing. So just a reminder, a refresher in case you weren't here, what are we talking about? We're talking about looking for a foreground object, in this case a black hole, against a sea of background stars. You want to look in the universe where the stars are densest, but that you can still resolve them individually. That's typically towards the galactic bulge. And the background star's light is gravitationally lensed by the foreground object in a transient way. Everything's moving, so this is a transient signal. It is a time domain project, fundamentally. Now, if we switch to looking at the observer's reference frame, if we could build an infinitely large telescope, what would a gravitational lensing event look like? Well, the foreground black hole, here shown with a slight shadow or glint, can't really see it though in reality, would gravitationally lens this background star, and you would see that star temporarily have two images. It would go from looking like one star to literally looking like two. You can play this game at home if you have a wine glass and you tilt it on its side and put a candle or a lamp behind it. You can suddenly see two images of the lamp. It's the same thing. You're familiar with strong gravitational lenses in the cosmos, same thing. Now, let me play that one again because, importantly, when this occurs, we can't resolve the two images for the most part. I'm hoping someday Shemek will show us some pictures of resolved lenses in the Milky Way, but we're not there yet. But there is a signal that we can see. When you integrate all the light from both of those stars, it turns out for microlensing, surface brightness is preserved. And during the event, you see how the star actually looks like it gets bigger over time in area. That results in a brightening temporarily. And then, as Peter said, it also results in an apparent position shift on the sky. Okay, let's get more physicsy about this. This is a now very famous animation. If you look up microlensing on Google, this is probably the first thing that will pop up by Scott Gowdy, which shows you the geometry. The black hole is the yellow star in the middle. The green circle is the cross-section. You have to get these two things close enough projected on the sky. That cross-section is called the Einstein radius. And then the two blue images are the double images that we saw going by. The red position is the background source star where it actually is, not where we see it. Now, that cross-section is called the Einstein radius, and it scales as the lens mass, square root of the lens mass, and the relative distance between the source and the lens. Those are the two key parameters to remember that go into the Einstein radius. So obviously, your cross-section gets bigger as your lens mass gets bigger, which is great. That's really good for black holes. Now, translating that into the photometry, if we add the flux of those two images together, that's what this little equation is here on the lower left, that produces this apparent brightening. Now, if the event is long enough, the apparent brightening is not so symmetric as you see here. It can have some wobble, some asymmetry, or some flared wings due to Earth's motion around the sun. That's what we observe with the vast majority, historically, over the last 20 years, of microlensing surveys. They're photometry, big field of view imagers. They're taking pictures of the night sky multiple times a night towards one pointing, usually the bulge. And they're seeing events like this pop off every once in a while. The cross-section is small. It's 10 to the minus 6. So we have to look at a lot of stars to find a microlensing event to begin with. And we can get this photometric light curve beautifully. But unfortunately, there's only two kind of main measurable quantities, the duration of the event and that microlensing parallax, which leads to that asymmetry of the light curve. So those two quantities are what we get out of the light curve alone. And unfortunately, they don't give you much information about the mass of the lens. And that's because the duration is the Einstein radius, great, the mass is in there, but it's divided by the proper motions. And so if two stars are moving slow, they can, with respect to each other, they'll look like a long duration event also. So this is where the astrometry comes in that Peter explained yesterday. I won't go through this in too much detail. It's much more complex. Again, you see the two images, that's in yellow. The actual source position is in green. And then what we see when we make a measurement is what's in red. It's that little tiny deviation from a straight line trajectory. The amount of that deviation is given by this quantity, this delta C, and it's proportional to the Einstein radius and nothing else, which is nice. It is fundamentally encoding that mass and the relative distances. And that's what we need to get our mass information. So if we can measure that astrometric signal, that small perturbation, we can actually constrain the lens mass. How big of a signal is this? It's not huge. If you're an observer, you'll realize this axis, which goes from 0 to 1 milliarcsecond, is quite tiny. It's a challenge to make such measurements, even with Gaia. And so the nice thing, though, is that it's a relatively weak dependence in mass. So yeah, we're talking about black holes, which should have 1 milliarcsecond signals, but even neutron stars and stars will be detectable with Raman through microlensing. Okay, so I said that black hole microlensing, or microlensing in general, is rare, and it's hard to measure. So where and how do we look? If it's hard, we have to be very prepared. And so we do that. So, you know, like I said, there's been these photometric surveys that tile the sky, or not all of the sky, the parts that are in colored patches there. They are finding about 1,000 events per year. Not all of those are going to be black holes. Which ones are the interesting ones? And again, I think Peter touched on this yesterday, but this is why we have to go into theory to figure out exactly which events to follow up. So we'll launch into what we need to know about stellar populations, and in particular, how stars turn into black holes in the initial final mass relation to figure that out. So Peter had an intro slide on Popsicle. I'm going to go into this in a little bit more detail. So this is a code that we built to be able to make predictions for what microlensing surveys should see and which ones would be good candidates for black holes. So we're making a mock Milky Way in a computer. We start with a typical Besançon model, although these days we can get more complicated. We can, you know, drop in bars, change potentials, do whatever we'd like. Unfortunately, those simple codes that mostly exist don't put in the compact objects. They put in stars, but there's no compact objects. So we have to add back in the compact objects, black holes, neutron stars, white dwarfs. We have to, in order to do that, we have to understand stellar evolution and the stellar initial final mass relation. We have to give these new compact objects positions and velocities. And then finally, we have to figure out which ones cross-match. We have to run a survey on this mock Milky Way for 5 years, 10 years, sample like we would in the real data, and figure out which things actually cross. Now, I glossed over a ton in here, and I will kind of bring back little bits and pieces of this population synthesis as we go in the form of questions. So the first thing, the simple thing, the thing we started with was single populations, all single stars, right? We just assumed all black holes were single to begin with. Okay, not so bad, 90% probably singles, so it's probably fine. And when we ran that simulation, what we found is that the black holes all have long duration microlensing events. This is the histogram of microlensing events now coded, because we're making a mock Milky Way, by what their type is, a star, black hole, neutron star, white dwarf. And in red, you can see the histogram of the black holes. Their microlensing durations are all, it's kind of peaked around 70 days and extends to this high end tail, 100 days, 150, 200 days. That's great, but I wanted to point out that these distributions where the neutron stars and black holes fall is very dependent on the input physics. The things that matter the most are the kick velocities, as Peter showed in his movie yesterday. But there are other things too. There's a lot of things that are dependent on extinction laws and how many stars you can actually see when you're looking deep into the bulge, what the survey spatial resolution is. There's a bunch more that goes into it that's observational in addition to the physics. Okay, so now we look at long duration events. Those are the ones we want to follow up and get astrometry for. After we did this work, we actually realized that the duration was not the only thing we wanted to look at. Peter showed this figure yesterday, which is the duration on the horizontal axis, and that microlensing parallax, which is basically the shape of your light curve, the asymmetry of it. You can see everything separates really nicely in this space. The black holes are down on the lower right in our mock catalog. And I wanted to show you the physical direction things move in this space when you change something in the simulation. So everything, if you give it a kick, it moves to the left. If you increase the mass, it moves down and to the diagonal. And if you change the relative parallax, you separate things more, then things move up and to the right. So this encodes galactic structure, kick velocities, and mass functions. Okay, and of course, as Peter mentioned, the best black hole candidates would have not only long durations, but this low microlensing parallax, if we could measure it in time to get astrometry. So inside of Popsicle, we had to be very careful about what we turned from stars to black holes. And so we knew that the old school, draw a line in an initial mass and call everything after that a black hole wasn't working. So we've actually encoded up several different initial final mass relations. Popsicle is meant to be a forward modeling tool that you can eventually run inference on. So we wanted to code as many different available initial final mass relations as possible. So we started with Reifel and Suchbold, and we have a few more in there. If you're a theorist who likes to make models for IFMRs, please let us know. We'd love to add yours in here too. That way we can test them all against each other, which is really nice. It is probabilistic. For every star, it is not deterministic whether it turns into a black hole or neutron star. Sometimes it's a black hole, sometimes it's a neutron star, and we encode those probabilities inside of the population. So with this code, you can also ask, what is the black hole mass distribution? This is mostly a function of those initial final mass relations. Everything else is sort of observational completeness, which is baked in. This is what we had at the time. This is from 2022, based on 3 different initial final mass relations shown up there. And you can see, okay, so Reifel was solar metallicity only, so it has this hard cut at sort of 17 solar masses. That's probably not believable. Suchbold has sort of the same set of models, but now run at low metallicities as well. So encoding now the halo and the low metallicity bulge stars that produce black holes. Those should be in there. And then Spera, you can see in blue, also has low metallicity black holes, even lower metallicity and more massive black holes as well. So this is what you would get of the mass function if you were to do a microlensing survey and measure all the masses of all the black holes, right? That we could see and detect with something like OGLE. It's a big difference. So my point here is that the microlensing surveys can be very sensitive to the initial final mass relation because they can measure the mass function in a way that is comparable to what the gravitational wave sample gives you, but now for the bulk of the population. You might notice the weird little spikes. That all comes from the initial final mass relations, the supernova simulations. At the time, they would produce these little islands of unexplodability and explodability. In this case, is the unexploded ones that you get this spike in black holes suddenly. Whether that's real or not, who knows? Got to run more supernova simulations. Okay, So back to our questions, and what can we answer about them, at least from a theoretical, make some predictions here. So first, the total number of black holes in the Milky Way, based on this mock Milky Way and propagating through star formation histories, we expect about 200 million black holes in the Milky Way. What stars turn into black holes? Well, you saw those initial final mass relations. It's stochastic. Stars above 20 solar masses, but it's not all the time. Sometimes they turn into neutron stars, sometimes black holes. At least that's the prediction. How are binary systems formed and destroyed? We updated more recently Popsicle to include binary systems, binary star systems, binary black holes, neutron stars, white dwarfs, all of it. And we said how many of those could be observed with microlensing. So Natasha Abrams has a poster that will explain all of that if you'd like to ask her more about it. But fundamentally, all black hole progenitors are born in binaries, and they may not be detectable as binaries necessarily. Some will be, some won't be, at least with current surveys. This is before Roman, okay? So with the current surveys today, although the underlying binary fraction, this is for all stars, not just black holes, is huge, right? That's anything with a B in it over there is a binary, and only the yellow are the singles. So you see more than half of all microlensing events that are observed are probably binaries. But can you recognize them as such? From current surveys without astrometry, it's actually quite hard to recognize them. Most of these single peaked multiples, those are actually binaries that just look like masquerade as single objects. So with today's surveys, binaries are hard to find, but they're there. With Roman, this will be dramatically different when we add astrometry, and I'll show you that later. Okay, another one. So this is another plea. We've built a population simulation that produces microlensing events and black holes, but in principle, I think we can also use it to do wide binaries. Right now, it cannot do tight binaries because we have no binary mass exchange built in, and we'd love to plug into some of the codes that do that and incorporate that. We definitely don't make gravitational wave predictions with this code. It would be nice if we had a code that could do all of those things together and stitch them together. I think that's, again, one of the fundamental drivers for the extended workshop here. So if you're hanging around or you're not and you're interested in this, let us know. Okay, so let's get on to some data now from microlensing. I'm going to tell you a little bit about these surveys, but very briefly. There are lots of options. There are microlensing surveys today that have been looking mostly for exoplanets in the last few decades, but they are capable of finding the black holes too. They're probably finding 10 black hole candidates a year, but we can't follow them all up. It's very expensive to go get Keck time or Hubble time or JWST time and get astrometry for those black hole candidates. So we've only been doing this at a pace of 1 to 2 black hole candidates per year, and the success rate is expected to be about 30%. So if you want to know why we have only found one so far, that's why. It's hard work. We've only been doing it for the last few years, and we're learning how to do it as we go. And this 1 to 2 black hole events per year plus a 30% success rate means stay tuned. There's more coming very shortly, but it's slow work. Next generation. Next generation ZTF's been around for a while, but Rubin as well. Everyone's very excited about that. It'll be fantastic for microlensing photometrically. So lots of microlensing events, 10 times more candidates per year probably. But can we follow them up? Not easily. We can't do it even today with Ogle. How are we going to do it with Rubin? Gaia, you might think Gaia provides the astrometry for everything, right? No, these events are towards the bulge where it's very crowded. They tend to be fainter beyond Gaia's limits to detect. So Gaia's the predictions, they're all over the place for how many microlensing black holes Gaia will find, but it's going to be on order 1 plus or minus 1 when DR4 comes out. I hope I'm wrong. I hope it's more, but I think most people agree it's going to be a small number. So what are we all excited about? We're actually really excited about Roman. So Roman launches next year. I'll have more to say about it in a moment, but it's photometry and astrometry together at the same time. No more picking events, having to do follow-up and schedule it. We get all of the microlensing events with both modes at the same time. That's amazing. And so as you saw from Peter yesterday, the yields we expect are something around 500 black holes with well-measured masses. Okay, so let's talk about Roman in more detail. Who is not familiar with Roman? Doesn't know anything about it? Yeah, okay, good. I see a few hand wiggles, so that's good. So let me tell you about it. It's not an astrometry mission, as Peter said. We're hijacking it. It's not a black holes mission. We're hijacking it. We're taking it over and making it do what we want it to do. So we've taken over Roman. There's this beautiful survey called the Galactic Bulge Time Domain Survey, which I'll get to in a moment. But I forgot, I want to tell you the telescope. The telescope's basically Hubble, but with a much wider focal plane, an all-infrared focal plane. So it's a survey instrument. It has a field of view that's something like 0.7 square degrees. And it is, just look at the wide field instrument up there. It has an imaging capabilities from 0.5 microns down to 2.3 microns. 200 times HST with C3IR's field of view. So if you're an observer and you've used Hubble, that just gives you a sense of scale. Mission, so the launch is September 26th. That's next year, less than a year away. Mission duration, I put 5 years, but it's classic NASA style. It'll live forever, if we're lucky. Okay, so the Galactic Bulge Time Domain Survey, it's designed to find exoplanets, but thanks to our friends in the exoplanet community, they've been very willing to let us find black holes too. This survey will image these 6 patches towards the galactic bulge. It will hit each patch once every 12.5 minutes. So 12.5 minutes cadence, down to 24th magnitude in HAB, so quite sensitive. It will do so for chunks of like 70 days in the spring, and then 70 days in the fall, with big gaps in between. And then it'll come back the next year and do the same thing. There is in the middle of the 5-year mission, there's like a 2-year gap where it doesn't do much, but there's a little bit of gap-filling observations that we've managed to wrangle out of the project. In addition to this, it does all of that at one filter, but every few hours, every 3 hours, I think, Hans Walters, it's something like 3, if you remember. Yeah, okay. It'll take another 2 other filters. So there will be color information that's time domain as well. And then most importantly, at the beginning and ends of the seasons, those 70-day seasons, all the filters in Roman will be obtained, including GRISM soil spectroscopy. What will microlensing events with Roman look like? Peter showed some light curves. These are updated versions of those now with the gap-filling observations that are planned. So you can see the 3 seasons, 1, 2, 3, that's spring, fall, spring, and then a gap filling where it's kind of coarse. That's why it looks like there's more scatter. We don't do 12-minute cadence there. We do 3-minute cadence. 3-day cadence. And then the gap is 3 seasons, and then it's back to the dense stuff after that. So this is a vanilla point source, point lens black hole event, 12 solar masses. You can see it's detectable in the light curve very easily. The astrometry, this is the RA as a function of time in the middle panel, and the declination versus time in the bottom panel. A very obvious microlensing signal. This is not a hard experiment anymore. This is with the proper motion and parallax removed, so it's just looking at the microlensing signal, and it makes that beautiful ellipse on the sky that you see. Very easy to measure. This is amazing, because we've been working really hard at this for a long time. Now, Roman is not just sensitive to isolated black holes. This is true for microlensing in general. So I wanted to show you some complex systems, because I think Kareem was asking about binaries in microlensing yesterday. This is a binary source. So the foreground black hole is a point object, it's isolated, but the background object is a binary star in the bulge, separated by a couple of milliarc seconds. Not a wide binary, but a somewhat wide binary. Okay, light curve still looks good. There is an astrometric signal there, you can see it, but when you look at the microlensing signal, it is wacky. So you were asking about, can you see the binaries? They look very different astrometrically, and that's a binary source. Okay, binary lens is also wacky. I don't have as clean of a picture for that one yet, but here's one that is measurable in the astrometry. The orange is the real model, so the second peak was not something that fell in a gap. It's something we wouldn't be able to see. And yet the astrometry still looks totally wacky, right? So these binary lenses, and this is in this case, this is not a binary not a binary black hole, but a binary star, low mass one. Even that half solar mass binary lens is detectable in the astrometry. The astrometry can be really wacky for binary systems, very easily recognizable. If you are interested in this and want to play around with things, we have a little calculator online that does all of this modeling for you, and you can go and pick what model you want, binary lenses, binary stars, slide some sliders around and have fun. There's a QR code you can snap a picture of if you'd like to play, and it's just a live web app. You can start to get familiar with what microlensing is going to look like. And then the last thing I wanted to show was there was a question about binary astrometric wobble, not microlensing at all. I said our population synthesis, we can examine that. So with all the caveats I mentioned, no binary mass exchange, our binary populations probably aren't as nicely robust as we'd like them to be. I thought I would put up just the period and observable semi-major axis, the astrometric wobble from, these are binary stars, black holes, everything. You can see they're marked here. And the zones that we can measure is everything at 0.1 milliarc seconds and to the left for sure will be easily measurable, right? So that's everything down to quite small periods, way less than a day. And then, of course, all the wide binaries. And there are some zones we'll have to worry about for detecting astrometric wobble. The 70 to 180-day periods are not well sampled because of the gaps. And long duration periods might need some filler as well. Okay, so that's just the one plot I wanted to put on astrometric wobble in case anybody was interested. And then finally, I'll close with the Roman Science Collaboration. This is a group that's wide open to everyone. It's a community organization that provides support and a place for you to talk about plans for Roman, plan proposals, learn about the technical information. You can join. It's very easy. It's relatively low investment, but we have some really fun discussions and meetings, and so that's available if you want to start getting your hands dirty with Roman. And I'll finish there with all these basic questions. If I've missed any, please let me know. I'd like to add them. And then, of course, none of this work is done in isolation, pun intended. There's a huge group of people who have been helping us with isolated black holes for the last decade, and there's a lot more to come, and we need all of your help. Thanks.
Yeah, thanks very much, Jessica. So, questions? Let's start.
Hi, I'm Majiran. So, I wanted to ask, what do you assume in Popsicle for the galactic potential and potentially its evolution for the galaxy?
Yeah, so we took a so it depends. It's a tunable parameter. You can run Popsicle with different potentials. We've taken a standard Bayesian model with a bar that's present and tilted more highly, not the less tilted bar, but the more tilted bar. But that's a parameter you can change. We don't time evolve it. We know this is a shortcoming we'd love to fix. However, there have been some papers sort of saying, well, like, we need to worry about black holes and neutron stars being puffed up. If the kicks are small, it's probably not that big of a deal. We put them where they should be with the rest of their stars. Yeah.
Hi. Awesome talk. Lieke van Son, Radboud University. You mentioned the 500 candidates per year, which is super cool.
That one's a total. The 500 is total, we think, per year. Just so you know, for Roman, right? Yeah.
No, from Roman.
Yeah, 500 total for the 5-year mission.
Okay, okay,
Yeah.
sorry. Okay, it's slightly less, but still super exciting. But I was wondering, you mentioned that a lot of the things in the Popsicle depend strongly on the kicks and the distributions, but that number seems to be pretty certain. Is that because, well, we don't really care, or is there secretly a big error bar on that 500?
Yeah, you're right. In the papers, it's order 500. It is not very certain. Okay. It's uncertain by an order of magnitude still.
Okay.
So it could be 50, it could be 5,000. I think the 500 is, we opted for a slightly lower conservative estimate, so it's more likely to be higher than that, but it depends on the underlying populations, the ISMR, you know, the kick velocities, all of it.
Okay.
Yeah.
Thank you.
Mutgul, my question is, on Roman as well. So what are the odds that you actually see the same lens, microlens, more than once? And is there any way for us to tell that it's actually the same lens?
Yeah, so those binary source lenses, that's essentially what's happening. It's a background binary star system, and the black hole passes over one and then the other, or, you know, it's not always in line, of course, it could be at an angle. So that's essentially what's happening there. Beyond that, the crowding, so Roman is quite high spatial resolution, so the crowding is not so much that you expect frequently to have second lenses. If there is a second lens event, it would be very weak. It's worth thinking about. I don't think we've actually done good looks at how often that occurs. If Roman has an extended mission, that would be worth checking.
Hans-Walter Rix, MPIA. Lovely stuff. I'm very excited. I have a question about the slide with the first Roman microlensing example that you showed. I guess the two related questions that I have is, A, what is the role of, yes, LSST Rubin in filling in the light curve in great detail? And secondly, looking at this, unless it's very carefully chosen, that would make me optimistic that Gaia could see that thing.
Yeah, so it's 18.6 magnitudes towards the galactic bulge. That's H band of 18.6. So the Gaia magnitude is significantly fainter than that, something a la 20, 21. So it's challenging. And in the region towards the galactic bulge where it's not so optically extincted, there's a little bit, it's very crowded for Gaia. So the astrometric errors grow quite quickly, much quicker than you expect at the faint end. So yeah, so this one it's a good detection. It's not great. So of the black holes, this is probably in the top 30% because it's massive. It's 12 solar masses, and it's a slightly closer one. So it's a little bit like 110462, the one that was been detected. Yeah, so in the gaps, LSST, so these are, remember I said Roman can observe in the spring and the fall. HST, JWST cannot observe in the summer towards the galactic bulge. So it's critical that you have ground-based coverage of the light curve. That's where Rubin and ZTF and LS4 will come in. And if you can do astrometry in the summer from ground-based AO, that would be great. So those gap filling in those summer seasons is the role of the ground-based observatories.
Hi, Jessica, Selma de Mink here. Exciting, and sorry for my voice.
No problem.
I should know this, but can you remind me what parameters we measure for a single event? And in particular, if we had a double event, what do we gain in what we know about the object?
Yeah, so for the single events, actually, the parameters are mostly listed at the top here. You learn about the lens mass, the relative parallax. You actually can, in some cases, I've removed it here, you can't see it, but you can actually measure the parallax directly from the astrometry as well. And you measure the proper motion, direction, and amplitudes. So those are the things you get for a single event. For a binary event, you get the mass ratios. For the binary, sorry, I should say for the binary lenses. So those are shown at the top. You get the mass ratios. So, and the lens, the total lens mass. So you actually get all of it. You get both masses. How well we can measure those, these models tend to be a little bit more degenerate. And I don't think we've really fully explored from the astrometric side of things whether all those degeneracies can be broken and at what degree. So I haven't actually looked at how precisely we can measure masses for stars with Roman astrometry, given like proper fitting and everything. For black holes, the masses are still extremely well constrained. We can also get separations projected on the sky, and then the bulk proper motions as well. Orbits, potentially, for short period orbits.
Well, Selma just asked my main question, and thank you for the answer. This is really exciting. We can't wait. But I'll ask a secondary question. So I think the binary evolution codes, hopefully the triple evolution codes, can couple with yours and place them in the galaxy. I was surprised by a statement or confused early on when you said that you expect the black holes to be mostly single. I expect the black holes to be mostly binary because they're coming from massive binaries. The binarity is definitely close to 100%, and they're hard to unbind. So I'm not sure I understand.
Yep. So this paper is one of several that have predictions using, now these are with actual mass exchange and binaries and kicks and everything. And so all the written literature I can find that have done the population census show this kind of 10-to-1 ratio of isolated to binaries. If that is not what you're finding, that's very interesting. We'd love a quantitative model to put into and see how it changes. We've run Popsicle where they're all singles and they're all binaries, and we can compare. It doesn't change the yields too terribly much, actually, but it does change what the signal looks like. If, of course, they're all
I think there can be a variety of predictions.
Yeah.
Just my 5 cents on this. Many binary systems merge, so you get a single star, and many of. That's right.
Or even just massive, huge mass loss, I think it can also unbind.
Okay. Hi, Jessica. This is Teja from UCSB. So if there is a as yet undetected tail of high kick black holes, would you serendipitously discover it, given your observing strategy?
Yes, as long as the kicks aren't too extreme. But yeah, the cadence at 12.5 minutes is plenty fast to see even, I think even the fastest, even 1,000 kilometer per second black holes, I think we'd still see. Yeah. They have to, pass in front of this Roman field, but yeah.
Hi, Jessica. This is Aparna Venkatesan from USF. If I understand this correctly, these black holes are in place within a few 100 million years of whatever star formation event. So that's interesting. If there's really 200 million black holes, I don't quite know what the distribution is. Strong lensing, the microlensing is a weak signal and often a one-time thing. But if, depending on their distribution, is weak lensing an option at all in our galaxy or other galaxies to constrain the distribution of quite so many black holes? Thank you.
So we've been thinking about this a very little bit. It has to be a close black hole. So the question is, could you find the closest black hole, stellar mass black hole, with weak lensing, even if it doesn't sit in the Roman field, with something like Gaia? And I don't know, does anybody who's done Gaia astrometry know if anyone's looked for a weak lensing signal? I think we have to know enough about the reduction pipeline to find it. You'd have to use many stars in an area and show that there's some slow transient signal over time. In principle, it's possible. And I think the signal could be strong enough if the black hole is close. It has to be within tens of parsecs, so like 10 parsecs maybe.
But these 200 million, thank you, the 200 million black holes would mostly be, where would they be distributed in our
Mostly
galaxy?
the bulge, of course. That's where, 20% of the galaxy mass, and then the disk is next, and then the halo.
Thank you so much.
Okay. Yeah, it's me. So I have a question about Popsicle. Is your code able to reproduce optical depth measurements or even rate measurements that we do with Ogle?
Yeah, so if you go look in Casey's paper and Natasha's paper, we have all the rate predictions, and they mostly represent what is seen for the optical surveys today in terms of optical depth. There's a little tension between optical depth and actual visible number of stars. So there's a lot of fluctuation depending on the field pointings, but I'd say on average it's actually pretty good. The TE distribution also, with the binary inclusion,
that was my other question about the TE distribution, because I remember that in one of the first versions of the code, the TE distribution didn't really match observations. So
yes, but that was a good thing, because the first round didn't have binaries, and so if the TE distribution matched, it would have been worrisome. When we added the binaries, actually the TE distribution looks really well matched now. Good question.
Okay. I had a question about the neutron stars. So it looks like you're assuming a single fast mode for the kicks in the standard simulations.
It's a Maxwellian distribution.
Yeah. But if you look at globular cluster neutron star retention or certain BE X-ray binaries, there's clear evidence that maybe 10% or so of them get very slow kicks. Mm-hmm. What would that population look like here? Would it be easy to distinguish those from white dwarfs?
Yeah, so they get in the midst of that crowd. Oh, I'm not going to be able to find this easily here. They get in the space where there's a lot of stars as well. So the neutron stars are the ones that are in orange. And so they're massive over to the right, but then they get kicks that way. So the slow kicks would actually move a little bit more towards the black hole cloud. Mm-hmm. And so maybe you could find them that way.
Okay.
Yeah.
Last question? Yeah. Johan Samsing, Niels Bohr Institute. Sorry if I missed this, but here you're looking at the free-floating black holes in front of the stars here, but you also have a lot of white binaries. Probably where one of the components is the black hole, right? Where you have self-lensing of the star that is in the binary. So I'm trying to understand what is the fraction of self-lensing binaries compared to just the free-floating population you're looking at. The
fraction of wide self-lensing binaries is very small, just because you have to hit just the perfect inclination. It has to be 10 to the minus 5 or 6 inclination. So that's pretty challenging. Close binaries are a little bit better, but that's also a rare phenomenon in general. So
so it's
depending
much
on
more
we get
likely
what
to just have something by random floating in front
we
of
might,
you than-
yeah.
Okay.
So we could look at what that prediction is. I remember doing this roughly for the self-lensing compact binaries, and it's pretty small, but I think the chances are good that we might find a couple, like black hole, white dwarf, self-lensing.
Okay, thank you.
All right, then we wrap it up here. Thank you very much, Jessica.
Thank you.